Today I want to talk to you guys about one of the greatest debates in Martian science right now. And that is there actually methane in the atmosphere of Mars? There has been an enormous amount of work that has been done on this. At the very least, 4 different spacecraft plus instruments from Earth have published results declaring that either they detected methane or they didn't detect methane. So we're going to break this down into a great amount of detail. If you already know something about this kind of thing and you just want to skip to a specific subject, I'll have a table of contents that will give you a feel as to where you can jump around into the video to wherever is your appropriate level. But we're going to cover this all in a really huge amount of detail. First of all, why is this important? Methane on Earth is typically found due to some kind of a biological process. So the detection of methane on Mars would be a really huge piece of information as to whether or not there is life on Mars. This would be huge. If they could really definitively prove this, this would be amazing. Now, it's not always found as a result of some kind of life. It could be found through volcanic activity on Earth. On Titan, there's methane all over the place. We don't really think the methane on Titan had anything to do with biology, but it is still a possibility, and this, of course, is the one that has attracted the most attention for the general public, that methane could be a sign of life on Mars, because who doesn't want there to be life on Mars? That would just be amazing. So we know about the why methane is important. Now, how is it that they're actually detecting this? To get to the bottom of this, let's explain how you identify any kind of chemical. If you're wanting to identify something, the most basic thing that you can do is to look at it. And that is one of the most common ways that scientists will actually do to try to identify what something is. They'll take a look at it and be able to identify it. Each mineral has some kind of a characteristic, although some of them can be a little bit confusing to the human visual eye. But if you look at it with a special instrument, you can actually break out the line and determine it all. And we'll talk about that in a moment. The second way that you could identify something is by its physical properties. Water is one of the simplest of these. It freezes at certain temperatures, it melts at temperatures, it boils at certain temperatures. So if you have a substance that is boiling at a particular temperature with a given atmospheric pressure, you know it's probably water. This is how Phoenix identified water ice on the surface of Mars. It dug a hole. It found some white type substance that appeared to sublimate away after a day or two. And that is exactly what ice would do. And so they pretty conclusively prove that there is ice. The third way is how it reacts with other materials. For instance, if you have something like gasoline, if you light it on fire at a particular temperature and it causes a spark, then you have a pretty good idea it's combustion. If you want to try to determine if something is salt, you can mix it in with water, and if it dissolves, then it's salt or sugar or something along those lines. If it burns away in the presence of certain substances, that's some indicator. All 3 of these are commonly done to identify minerals and substances on Earth, and in fact, this is exactly the same kinds of things that planetary scientists use to try to determine whether or not there's something when they're digging around. So how do the Martian ones do? Well, all of them involve something called spectroscopy. Now, spectroscopy is taking a look at light and figuring out what something is made out of based off of that light. How does this work? Now, to really understand this, we have to understand a few things about light, and then how light is created, and then how it reacts to some kind of a substance when it encounters it. First of all, what is light? Light is a stream of photons that is coming that has some given amount of energy and some number of photons. The more photons there are, the more intense that light is. The more energetic these photons are, the higher the frequency of the light. Visible light is pretty high frequency light. Radio waves is a very lower frequency type of light. But they're all essentially the same thing, just with different energy levels. Now, we're primarily going to talk about visible and infrared light. Visible light is light that we can all see. It's how you're able to see me here. Infrared light is light that has less energy than red, which is the lowest energy of visible light, thus the term infrared. Okay, that's easy enough. How is light actually generated? Well, there's basically 2 mechanisms that generate light that we're going to talk about for the visible infrared type regions. The first one of these is any object that has any heat will generate some background radiation. None of them are perfect, but the ideal radiation that it will form is formed by Planck's law. It has this nice little bell curve that you can see over here. How can you practically understand this? Well, imagine an electric stove. When you very first turn it on, the heat is essentially room temperature and it doesn't glow at all. If you're looking around in pure dark, you're not going to see very much, if anything at all. As the temperature starts to go up, you can see at first a very, very dull red. It'll start to glow, and soon it'll start to go towards a brighter red and maybe even a yellow type color, depending on how hot it is exactly. That comes from the fundamental heat. This is something that all objects undergo. I'm emitting some kind of infrared type light right now. That's how night vision cameras will work. They'll look for this infrared signature of people. This is the same way that incandescent light bulbs work. They have a very thin filament that they heat up to a very high temperature, and that high temperature sends a glow out. That's why they tend to be a little bit on the redder side, because if you get to too high of a temperature, then they'll tend to break. And the sun is at a very, very high temperature, something like 6,000 Kelvin roughly. No metal can survive a temperature that's that high, so you don't want to have it quite so high, but you can still get a lot of visible light with something that's a little bit redder, so they tend to go that way. Well, how else can you create light? The other way, you have to understand a little bit about how atoms are put together, and molecules in general. An atom has a nucleus that's composed of neutrons and protons, and has some electrons that are kind of spinning around in predefined orbits. These orbits have names like S, P, D, and F, and they contain a certain amount of energy for each one of these given things. These electrons, we kind of think of them all in a stationary type state, but the truth is they're bouncing around all over the place, especially if you energize it through some kind of outside external force. For instance, fluorescent light bulbs, such as are found around here, will energize this with electricity. They shoot it through a special tube that contains a gas that's sensitive to this. Now, once these are energized, they'll jump up and down in these electron states. And as they jump between there, they'll release a particular energy band that will correspond to this jump. Because these orbits are fixed, they have to be a certain amount of energy, then they'll have a very defining characteristic that will allow us to look at it. So if you take a look at one of these fluorescent light bulbs that's around me, through some kind of a spectrogram or a prism, it will have very sharp lines that define the energy bands that it releases. An LED works in a similar way, but it doesn't have as much to do with the electrons directly as it does with a particular characteristic of silicon that is far beyond what I'm going to explain here. But it works in the same way that you have jumping energy levels. When you have a molecule, it does the same kinds of things where it has particular energy, but they have far more complex orbitals than the simple S, P, D, and F that just a single molecule will have. And these more complex orbits will release a broader spectrum of energy. Assuming I haven't lost you yet, you understand how light is created. Now, what happens when it interacts with something? Well, when it interacts with something, there's basically three things that you can do. You can either be absorbed, you can reflect the light, or you can transmit the light. So the fact that you're able to see me is the light that's coming from around the room. It's bouncing off of me, reflecting into the camera lens, and that allows you to see me. The camera lens is clear, at least in the visible light, and it will transmit the light through there, although it may absorb some small spectrum that you can't see a whole lot of, considering there's only 3 colors in a typical camera sensor like this. My body is also probably absorbing some of this. It doesn't transmit the visible light at all, although my glasses will transmit the visible light. Some of the light, though, is actually absorbed by me, and that's why you're able to see some colors a little bit differently. Everything does this in the entire universe. Anything that has any kind of matter at all will do this. How does this relate to spectroscopy and detecting methane on Mars? Well, every single molecule will have some kind of a signature that will show what they look like. Now, you can see over here the signature for methane is defined by the NIST. You see there's two regions where it has a lot of ups and downs. One is about the 1.3-ish micron range, and one is about 3.3 microns, as you can see here in the zoomed in versions. Where is this actually interesting? Well, there's a number of different instruments on Mars that will detect this. Most of them operate in the 3.3 micron, but we'll talk a little bit more about that in detail. So how do most of these instruments work? Well, all of them have some kind of a source that is producing light. In most instances, that source is the sun. The sun is not a perfect black body, as nothing is, but it's a reasonably good one, and we understand the spectrum reasonably well. Now, the sun has some particular lines that it absorbs that correspond to elements such as hydrogen, helium, iron, oxygen, carbon, and others. And these defined lines are very well known and studied. You can see over here a list from Wikipedia that will show you exactly where these different lines are. So in order to analyze the composition of the atmosphere using spectroscopy, you have to do a whole bunch of things. First of all, you have to have a source. That's most of the time the sun. You take this source and you shine it through the atmosphere of Mars. So if you have a spacecraft, when you're just barely almost at the far side of the sun, if you're poking your instrument straight at the sun at that particular point in time, you can see the sun as absorbed through the atmosphere of Mars. And you compare that to the sun that is not absorbed by the atmosphere of Mars, and you can see some small differences. Now, spectroscopy is a little bit of a black art in order to find these really trace elements. The elements that have the highest amounts of, in particular carbon dioxide on Mars, will show up the strongest. The weaker elements don't show up nearly as well, though. And the amount of methane that we're detecting on Mars is very, very small. It's on the order of a part per billion most of the time. If you imagine a box that's 10 meters by 10 meters by 10 meters, 10 meters being 33 feet, 1 milliliter in 33 feet is 1 part per billion. So it's a very, very, very small amount that they're claiming detections on. So once you have these measurements, you take the known spectrum from the sun, or whatever source you're using. It could be another star, it could be a laser in the case of Curiosity. You take the known compounds that are in there, you model what they would be absorbing, and you can kind of pull those out of the values. And then you start to look for smaller and smaller minerals. And eventually you start to get down to the noise, and it's really, really difficult. And for something that is as rare as methane detections on Mars, that becomes extraordinarily difficult to detect. But you have to make these kinds of models, and if you don't make these models right, you won't get the right values. But they have a very definitive signature that if you can detect that signature, you're golden, and you just hope that the parts that absorb in water don't also absorb in methane, because there are a lot that are in common. You also hope that those are not done by the sun. So each one of the spacecraft that has claimed a detection on Mars has done so in a little bit different manner, and so let's explain them one by one. Let's start with Mars Express. Now, Mars Express was the first one of these to detect it. It has an instrument known as the PFS, the Planetary Fourier Spectroscopy, that will do exactly what I said. It points at the sun, and when it points at the sun, it will get an idea as to what the background spectrum is. Then it will point through the atmosphere of Mars. You can detect the composition of the atmosphere over that one particular point on the surface of the planet Mars, in this instance, at that time. How well does that actually work? Mars Express had been at Mars for a long time before they claimed a detection of methane. They basically took some of these spectrums, and to really, really look at some of these rare chemicals, they averaged them out over a lot of time so they could reduce the noise that was in these images. They could improve the signal-to-noise ratio. And when they did that, they had 5 different features that were on the spectrograph that didn't quite make sense, according to the known model. One of these corresponds to a point where methane is absorbing a lot of the signal, so therefore it could in fact be methane. They didn't see methane in anything but this one-wave detection. So They claimed detection. They saw some variation across the planet Mars in this value. You can see some variation of time as they were moving across the planet, but it's still pretty curious. And as they've continued to work for 20 years roughly, they've seen some variations that appeared to be seasonal. They really needed, though, to have more than a one-band detection, because a one-band detection of methane isn't really that great, and it wasn't the greatest of bands. Scientists who study the spectrograph like to use something called a wave number instead of using the pure frequency. They're directly related to each other. In fact, all you do to get a wave number is you take the wavelength and you invert it, and you have a wave number. Usually the wave numbers are expressed in terms of centimeters inverse. But that just allows them to use a number that is much more manageable rather than something as tiny as 3 microns. They can say wave number 312, and it allows for communication that's very, very easy. You can see in the spectrograph that the biggest absorption happened at wave number 3012. Now, this is a part where the sun doesn't produce a lot of energy. This is due to the sun. Wave number 3012 also corresponds to the strongest absorption peak of methane. Unfortunately, you can't really use it because it was warped by the sun, and that reduces the signal-to-noise ratio quite a bit. But the nearby 3018 also is absorbed by methane, and it's not absorbed by the sun. So something strange is going on there. You can see some variation that happens over time, as these multiple plots will show. So there's something there. It's really hard to absolutely definitively say it's methane, though, because they don't see any of these dips in any other frequency that happens, and there should be more than one frequency, as you can see from the NIST data here. In order to really confirm this, they had to have a second band of detection. The first thing that they thought is, well, we could use some telescopes from Earth, point them at Mars, look at the reflected light, and in reflected light you're not going to see the terrain as much in the infrared. They use telescopes such as Keck that's high up in the Hawaiian mountains, or Sophia that's actually an airplane that can fly up really high, and they imaged Mars with this, and they saw a dip that corresponds to methane, and it's really not in a lot of doubt that these telescopes detected methane. But the source of this methane is in a lot of question. These instruments all operated inside the atmosphere of Earth. In order to take that out, they had to model the methane that they were seeing from Earth, and it could be that these estimates were off just a little bit, which would lead them to falsely declaring methane on Mars. They did see some variation on region and also seasonal variations based off of the Mars seasons, so it seemed a little bit plausible, but these were always in a lot of doubt. So, okay, how else could we get a unique band of detection? Well, Mars Global Surveyor also had a spectrograph that was very, very similar to the PFS, but it operated at a different waveband. It wasn't as high of frequency spectrometer, though, as the one that PFS was. Its resolution was about 6 nanometers, which is not particularly high, but they looked at the Mars Global Surveyor data, and they saw what first appeared to be a methane peak, as you can see over here. Now, later papers have since redacted that claim. They believe that they saw variations of the levels of methane over the surface of Mars, but they have completely redacted that claim, and they have basically said that there's not enough data to definitively prove whether or not there's methane based off of the Mars Global Surveyor data. It took them 5 years to do that, unfortunately, but there you go. These plausible detections of methane on Mars were leading to a lot of interesting data. Nobody really knew whether or not there was methane there. So they wanted to send some dedicated instruments to Mars to be able to prove one way or another whether or not there was methane there. There were 3 spacecraft that had instruments designed to detect whether or not there's methane on Mars. The first one of which to be sent there was Curiosity, which is a rover, landed on Mars in 2012 and has been traveling around Gale Crater. It uses a little bit different of a method than some of the other spacecraft. Because it's a rover and it can directly sample the atmosphere, it actually has a special laser that points at the samples that it takes from the atmosphere, and it can vary the frequency. It's called the Tunable Laser Spectroscoper. And using this, it can determine exactly what it's made of. These measurements indicate that there is methane on Mars, but it's still within the noise boundaries and that it varies seasonally, which is a little bit strange, and we'll talk about that more later. Of some particular note, though, is there's been at least 3 instances where Curiosity has detected a level of methane that is so far above the noise threshold that it has certainly detected methane. But these have only been 3 of these plume measurements that have happened, and there may have been more. There's only been 3 that I was able to identify. The most recent and largest of these happened in June 2019. It's just pretty curious, and we still don't know exactly what was going on there. Although they sampled it a day or 2 later and they were not able to reproduce the values. They still had a slightly higher than normal background, but it was essentially their background levels that they're detecting that are only a little bit above the noise threshold. The next spacecraft to head towards Mars to try to determine whether or not there was methane was sent by India. The spacecraft was known as the Mars Orbiting Mission, MOM, and it had an instrument specially built to detect methane. However, once they arrived at Mars, they determined that it wasn't able to distinguish methane from other similar compounds, and it hasn't been able to give any definitive results. The final one of these instruments was the ExoMars Trace Gas Orbiter, Teego, which has 2 instruments on board that should be able to detect whether or not there is methane. They only arrived in 2018, but they have not been able to definitively prove there's methane. In fact, they say that the upper limits are about 50 parts per trillion, which is considerably less than some of the other spacecraft that are observing it. In particular, Curiosity says that there's something on the order of 500 parts per trillion. Now that we understand all of these various spacecraft and what their results are, why are these results strange? What is unusual about them? The first oddity is that they vary seasonally. Now, why is this strange? Several chemicals in the atmosphere on Earth, such as water vapor, vary seasonally. In fact, they are known to vary seasonally on Mars. So why wouldn't methane vary? Well, methane is not able to freeze or liquefy on the surface of Mars, so it should stay a gas the whole time. The atmospheric models that we have of methane on Mars show that it's to stay around for 350 years, which is both a long time and a short time. You see, what essentially will happen is methane will eventually rise to the top of the atmosphere of Mars, and a very small amount of it will leak. That is the highest energy portion based off of the temperature of the planet. Some of it will also disappear due to solar radiation that hits the methane that will cause it to ionize and go off and do something else. Now, these are very well-known quantities, and we know exactly what the lifetime should be, and that lifetime should be 350 years. If we were going to have a seasonal variation, you'd have to have something that was a lifetime that was closer to less than half of a year. Huge, huge, huge difference, and we're not seeing anything remotely like that at all. The second thing that is odd is these plumes. You have various regions that seem to have methane and others that don't. The atmosphere of Mars is such that the methane should get distributed within maybe a month or 2 across the entire planet, and you shouldn't have these regional variations other than a very short transient phenomena. You should, in theory, be able to detect these background values from anywhere on the surface of Mars, therefore, of anything that's older than a few months, but ExoMars Teego has not actually been able to observe anything yet, so there's something really funny going on that we don't understand. How do we actually make some sense of this? What could possibly be happening? We have 2 spacecraft that have some really, really good abilities to detect methane. They're giving very, very different results. So let's talk about them one at a time. First of all, Teego could be broken. That seems pretty unlikely. The spacecraft was specifically designed to do that. They have 2 instruments that are doing that, and they are able to identify other compounds that they should be able to. So it seems like it's working just fine, and it doesn't seem likely that it's broken. Curiosity could be broken. That also is pretty unlikely. Curiosity is using the absolute best instrument of any of these to detect methane, and it's doing it in situ. So if it's saying there's methane there, then it's detecting some kind of methane, especially if it's well above its noise ratio. Although many of the measurements that it is reporting are actually fairly close to the noise limits, so you have to keep that in mind. The uncertainty for many of these measurements, depending on exactly how they do it, is around 600 parts per trillion, and they're actually only seeing a little bit stronger than that, so it is possible this is just noise. Now, we have to get into some more exotic things beyond here. We know that Curiosity is detecting methane, at least in these plumes, and we know ExoMars has not seen anything so far, which indicates a couple of interesting things. It could be that Curiosity is somehow the source of the methane. How would Curiosity be the source of the methane? Well, it has some pockets of Earth air, and Earth air, as we know, has methane, so it could be leaking that somehow into the detection ramp. It's possible it's doing that, but that doesn't seem particularly likely. But it is a possibility that we cannot discount. The second possibility of some interest is that there's some bacteria that is growing on Curiosity that is releasing methane, and when the sensors are oriented a particular way, the wind is a particular way, then this methane leaks into the sensor, and that is the source. Now, that to me is a lot more exciting, and that in my mind is at least plausible for a source of the Curiosity detection of methane. Now, you wouldn't be able to see this from Teego because it's not looking for a very, very localized source. You would be able to see it only if it happened to line up right over Curiosity, which isn't that likely. It could be that Curiosity is actually creating methane by its pressure down on the rocks. There are some rocks that when you put a little bit of pressure on them will release a little bit of methane. Now, you would think that we would have already detected these rocks that are in Gale Crater somehow by some other means, such as the sampling that it does. But this is a theoretical possibility, and this might be one of the more likely ones. The last ones all involve there being some sort of a source of methane at Gale Crater that Curiosity is detecting sometimes, and that for some reason it's either not going anything beyond Gale Crater, or there's some mechanism for destroying the methane that we don't fully understand. They've actually done analysis though, and methane, because it is lighter than carbon dioxide, should rise up to the top of the atmosphere and be spread around the entire planet Mars pretty quickly, so it seems really unlikely that it is not spread around everywhere. But what could some of these sinks of methane be that are destroying methane? There's a number of them that are discussed. The two most promising in my mind is either it's some kind of a dust devil, so a dust devil is kind of like a tornado of dirt. You see these in Arizona, you see these on Mars all the time. These dust devils will create a little bit of electricity, and that electricity could cause some of the methane to become ionized, which could cause it to react with something and fall. This hasn't been proven, and we don't have any real way to test this if it's happening on Mars, but it is a curiosity. The second of these ideas has one of my favorite scientific experiments that I've ever heard about. These scientists took rocks that are known to be found on Mars. They ground them up into a sand. They put the sand into basically a test tube. They vacuumed out the atmosphere such that it had the same composition and pressure of the Martian atmosphere, or in some instances they put in pure methane just to see what would happen to the methane that was there. And they put it in a tumbler for more than a year. The amount of patience that these scientists must have must be crazy, that they're sitting there in their lab seeing the sample tumble for over a year to get the scientific results that they're looking for. But they published a number of papers that are really, really interesting, and they have concluded that methane can actually become destroyed based off of sand moving across the surface of Mars. And what's moreover interesting, they found a way that you could kind of sort of test this on Mars. One of the smaller gases that's known to be on Mars is Xenon, and they tested this with Xenon in particular, and it had a little bit of a glow that could be seen if it was dark enough. So in theory, Curiosity could take a picture at a spot where this is more likely to happen, and if they see the right kind of a glow, then they have a pretty good sense that this is actually happening on Mars. Xenon has a higher energy requirement to pull off an electron than methane does. So if this is happening to Xenon, it probably can happen to methane as well. Once you've done this for a long time, you have some kind of a compound that has fewer hydrogen atoms than methane does. What happens from there? They took this air and they mixed it with some kind of perchlorates, some items that are known to be on Mars that have some chlorine. And what they found is they created a chloromethane where they replaced some of the hydrogen atoms with chlorine. Now this is a solid. Where this is really, really exciting is Curiosity has actually found chloromethanes on the surface of Mars. These were not expected to be there. Viking discovered these, but they didn't think that they were real. They thought it was some kind of contamination from Earth, but they're known to be on Mars, and so that's a really, really interesting find. So it could be that any methane that is created or released is somehow converted to these compounds, and there you go. So I've given you all of the scientific data. Now I'm going to give you a little bit of my own personal opinion as to what is happening here. Let me say, one of three things has to be happening so far as I can tell. Either Curiosity is creating the methane on its own, or there's such a small amount of methane that's being released on Mars that's right at where Curiosity is that it just happens to be picking it up, which seems very, very unlikely. Or that there is some unknown sink where the methane that is created on Mars through these random plume events will eventually be converted into something that isn't methane within a very short period of time, far, far smaller time than we expect to, by about 1,000 times. Which one of those three is happening? Well, I don't know. And now I'm going to get to a little bit more speculation. I think that the scientists jumped on this as a possibility, perhaps a little bit more to the public than they should have. These detections are always at the very threshold, and I've read all of these papers, and they always seem very, very confident in their findings. I saw someone who said 99% chance sure that there's methane on Mars. These values varied wildly, and just it seems a little bit odd in retrospect, although I have the benefit of 15 years worth of papers that I read in order to make this determination that they simply didn't. But the bottom line is if I was going to go with anything, I think Curiosity is creating the methane either from its traveling or some kind of bacterial life is occasionally putting a little methane that happens to live on Curiosity. And that's what it's detecting. And the truth is there really is essentially no methane on Mars at all. But I could totally be wrong. Time will tell one way or another, and hopefully we'll find out really soon. Thank you guys very much for joining me and for all of your support. This really was made much better because I had some people that were joining me in my Discord and helping me with various sources. So thank you to all of you who helped me to collect this data and to my patrons that helped to really continue my efforts going forward. You guys are amazing. Thanks. Let me know whatever questions or comments you guys have. Let me know what you think about methane on Mars. And until next time, keep on tracking. Take care. Visible light is the light that we can all... Okay, so there's... The first one is through... Now, where is... How can you... But you don't really want to... No metal. For instance... An LED light works in a similar way, but it doesn't release all bands of energy. It just releases... When you have a molecule, it also has defined orbits that are far more complex than the simple S, P, D, and F. It can also be... So how does this relate to spectroscopy? Well, every single molecule and will have some kind of a... What we have to do to determine whether or not something is in fact on Mars is you take this known source, being the sun in most instances, you have to... So in order to determine whether or not something is actually on Mars, 1 part per billion is like taking 1 milliliter, which is just a few drops really, and comparing that to this entire home. You know, my home is about 1,000 square meters. Most homes are maybe... It has an instrument on there known as the planetary Fourier spectrum. The Mars Express team, you can see in the spectrograph, but it is still kind of interesting that the most likely, the way, but these values, why